Okay, I'm Ronny Bull. I'm a professor at Utica College. These two are my students, Sean and Aaron. They did this stuffer as a project for a class of mine. Basically, I kind of challenged them to see if they could do this, and they accepted it. So I'm going to let them take it from here and then present to you guys the stuffer.
Thank you. So before we begin about the stuffer, it would be give you a quick rundown on what a TCP header is for those who need it. So the TCP header deals with the transport of the packets sent along the internet. So, it has the source, destination, where you're going, where you're coming from, size of the window. All we're concerned about are going to be two things: the reserved and padding. Those don't carry any data, while the padding is small bytes 6, and the reserved 6, padding is variable. But yeah. Typically, they don't carry any data. If you look at the documentation, they're reserved for future use. So that means we can play with it. So the stuffer is a packet stuffing. You can count how many times I say stuffing. We'll take the padding and the reserved sections of said TCP headers and send them along the internet after we stuff them with our own information. So what is stuffer? This is it. Run in Python with the help of Scapy to do all the heavy lifting for us. All we're doing is making a packet, putting our own data in it, sending it along where we want it to go.
The code is on GitHub. You do not need to take a picture of the slides.
So yeah, this is our first prototype, proof of concept. Our demo's gotten a bit out of hand since our project. So you'll see that in a minute. But yeah, so we're doing a demo now, or?
Okay, so I get to talk to you about the practical applications of this thing that doesn't seem very practical at all. That's my favorite part. So one of the most common scenarios to use this is once you've hidden information in the padding and flagged the reserved bits so that you know to look for the information while it's there, you can actually set up a lot of covert data channels between two people who both know that the program is installed in their computers. We'll come back to those that don't later. So you can actually set up a hidden channel in which you can pass surprisingly large amounts of information on things like video streams over existing internet connections, specifically any sort of TCP socket. Now, this has the benefit of not being picked up by most firewalls because nobody does deep packet inspection to see whether or not you've played around with the reserved bits and whether or not the padding is actually zeros. So you can actually hijack existing data streams inside of a network which you've already exploited, get communications going through, extract files, send messages. There's no encryption built in, but I suppose you could encrypt your text before sending it through, either with a cipher or anything that actually counts as encryption. But we don't have to worry about anything such as data integrity because we use TCP instead of UDP, so it's all guaranteed to arrive there in the correct order. If it doesn't, it gets sent again, which is great for us because we're lazy. We don't want to worry about that, so we let them take care of it for us. Now, when it really starts to get interesting is when you start getting into things like botnets. Now, one of the easiest ways to realize there's a botnet on your network is when the botnet starts to reach out to command and control servers to find its instructions. Now, the thing is, if it's just reaching out to a normal website and downloading a giant text file that's a PowerShell script, you kind of start to catch on that something sketchy's going on. But if you instruct your botnet that if I send you this particular section in the padding, you can hijack existing streams going into that user's machine, because assuming you've compromised somewhere upstream as well and can insert the data. So your botnet can actually read information carried along existing traffic that the user themselves is doing. So anyone even looking at their computer can say, oh yes, he opened up Facebook. But your botnet knows to look in that information, see that the reserve bits have been flagged, read the padding for its instructions, then carry them out. And there's no extra traffic at all, which is kind of cool looking because turns out companies that read the instructions for how to implement things such as TCP really trust that you're not actually going to touch the reserved bits. I'm not sure why they trust us because, well, once you play with the reserved bits, you can do a lot of dangerous things, but you can. You can also poach entire websites through this. We can't get this demo working here today because we did not want to rely on the internet of a convention center that a bunch of hackers are currently in, because we know better than that. But you can actually push basic HTML web pages over an existing connection. So if you have a web server of a rather popular blog and you want to hand out information covertly, you can have people navigate your blog with the program running and actually have an entire second web browser grabbing the second website on top of your existing website, and no one else is any the wiser. My personal favorite, though, is when you compromise something such as an upstream router on a network without compromising the client machines, because you can start actually grabbing information as it flows through and extracting it covertly. And you can also do what I have decided to call session-based denial of service. I'm sure somebody has an actual name for it because most things have been done before. But you can actually, because you're messing around with the information, if you don't very carefully modify the packets, you accidentally invalidate the checksums. And you can invalidate the checksums by playing around with the reserved bits. And if you change the reserved bits, then don't fix the checksum, every packet gets dropped. And nobody will really realize why, because nobody thinks to check the reserved bits. That's a recurring theme of this entire talk. Please check your reserved bits because people will play with them and then break your things and have a lot of fun doing it. So now I'm going to have my lovely assistant here take over the computer, and we're going to show you and point at things and say this is what actually happens and do some demos locally because we don't trust the Wi-Fi. Would you like to take over the computer?
Yes.
All right. Oh, yes. Actually, let's finish up the last few slides. Cool. So, right now, the thing about Stuffer is it's more of a concept than an implementation. We do have demos, obviously, because people like to see things work. But it's more of the concept of playing around with the TCP headers and inserting information into them. Right now, it's running Python 2.7 because all of the actually good libraries run on Python 2.7. You can port it over to Python 3. Scapy does work. A few of the libraries which work with Scapy don't work, but that's a issue for someone else. And also one of the things we really played around with but couldn't quite get working and no way to demo it anyways is actually routers such as pfSense. If you have any of them running at your house, I'm sure a few of you do, we're all nerds, can actually read the reserved bits as they flow through, and if the packet has been played with, either A, switch them back to 0, which would preserve your existing data stream and really annoy whoever's trying to do anything, or B, just drop the packets entirely, which is a slightly more aggressive solution, but I suppose if somebody's trying to hijack your traffic, you probably don't want that machine communicating with the internet no matter what, regardless of whether that current packet has been played around with, because they have something on their computer you don't want them to have. All right, so we do have a GitHub link. It's very simple. You can write it down. You can take a picture of it. We'll be dropping code up there as we get all the examples put up in there that we used today. The demo itself is fairly simple, not too complicated, because again, we don't trust the hotel Wi-Fi at a hacker convention. We've been to DEF CON. We don't trust you people. Give you all a second to write down the link, which is actually, wow, that's a really simple link. I like that link. Didn't even have to use a URL shortener. All right, now you can take over the computer and load up the demo. Yes, I'm positive this time. Clear out the screen so we can show the usage of the commands. This is my very Matrix-themed color scheme for Kali. I hope you all appreciate it. It's really fun when you sit somewhere and run some sort of exploitation tool and some random English major looks over your shoulder and wonders what the hell you're doing. All right, so left-hand side will be the receiving, or actually, first show them the actual original packet. So run that one with, nope, you want to run that with the, there you go. Use the up arrow. There are actually instructions attached to the program itself. If you run the program without any sort of flags, it will yell at you. It's very well built. I tried. Okay, so you ran that one. You went through and, okay, so the part we should be looking at is specifically the, can you step off the, okay, good. Couldn't quite reach the point. Okay, so this is a TCP packet going from loopback to loopback because, well, of course it is. Checksum is normal. And right up here we have the not shown reserved bits because of course we don't. Oh, there it is. So the reserved bits are currently set to 0L. For some reason, Scapy decides to translate the binary for 000 to just 0. When you see it changed later, it will be 7L because that's 111. And you can see that the padding for the packet is all just zeros over and over and over again until it reaches the default length it should have. This is fairly long because there's no actual information carried in this packet. Normally it'd be much shorter. So now, if we go over to the other side of the screen, we can actually start sending information. Yep. All right, so you can see it's just waiting for you to enter whatever data you want to send across. And on the other side of the screen, it doesn't actually have to be cleared. He can send whatever message he wants. All right, somebody name a word. Anybody? Hello. Sure, send hello. Oh, wow, hello world. Very, very cliched of you. Thank you. So now you can see that the reserved bits have actually been flagged, so the program knows to look for it because there is actually other traffic being bounced around on this normally. We don't want to review all of it. We don't care what's in all of it. We only care about the parts we played with. So you can see that we changed around the reserved bits. So now it's 7L, which is just 111 binary 7, translates over. They did it for humans to read. Unfortunately, we're not humans. So now you can see that down in the padding, can you just hit enter a few times to scroll down, Control-C, exit out of the program, then hit enter a few times. And now you've cleared out the example. Send something again. Then hit enter a few times. So we can see. All right, there we go. So now you can see that it actually carries across the message inside of the padding. The rest of the padding is still filled in with zeros because if you don't fill in the padding, things get very, very confused. But now that you've actually carried the message across, you can see that it's there. The rest of the information is all still the same. It still uses all of the same ports, all of the same information. The checksum has been changed since it got filled in. So yeah, it's very nice. It's good for transmitting information over existing applications. Now, we don't have I'd love to be able to show you the website, but we don't actually have Wi-Fi at the moment because the Wi-Fi is awful. So yes, is there any other comments you would like to add? It's not the most complicated talk on the planet.
No, it was very quick, actually.
It was very quick, actually. So yes, do we have questions? You do have a question, yes.
Could you go back to the all of it slide and then maybe just talk about the code a bit?
Sure. Do that.
Do you want to open up the actual code we're currently running instead of the old code we're not currently running? Yeah. All right, so this is the most recent version of the coding. You can ignore that one import of threading. It does nothing. So yes, so what we have here is we have, scroll down a bit so they can see the menu itself and we can work our way up. So right now we have just a menu being created and then it chooses whatever options you want, and then assuming you want to receive packets, which is in my opinion the more interesting of the two options because changing things is very boring, you can actually go. We are using the sniff function of Scapy to grab all of the packets which are actually incoming or outgoing, but in most cases it really doesn't matter because you want to see both the incoming and outgoing traffic because you care what you're saying as well as what they're saying. So it sniffs all the traffic, hands it up to the declutterer. Declutterer just checks to see if the reserve bits have actually been changed to the 7L, which again translates to 111 in binary. And then if it does, it prints out the message. It also, for convenience, for the demo's sake, removes all of the extra bytes that we don't care about, the random -0x or -x zeros. That way we can read it more easily. Now if I scroll up a little bit further, you were way down there. All right, we can see that a little bit further. We want to show them the one that actually works. All right, so basically this is our little function which demonstrates sending the information, modifying the packet with Scapy. This is not the exact one. This is to create a blank packet and send it. The one to modify them is slightly different, but this will do. So all it does is quite simple. It actually just grabs your message. It creates the packet with the reserved bits changed. It creates the padding. It actually overwrites the padding twice. That's weird. Okay, whatever. And then it just adds in your message. You can actually overload the padding of a TCP packet and send it over the network. We've had no issues doing so. I wouldn't personally recommend it because it could start to explode things, but it works. The actual library does check to make sure you're not doing that. And then it adds on the extra information to make sure that the padding is of the correct size. It's not too small because for some reason it cares a lot more if the packet is too small than it does if the packet is too large. I'm guessing that's because you can actually enable things such as jumbo packets. So networks have learned by now to not be too surprised when packets come across that are larger than they technically should be. So yeah, then it just fires it away over the network with no issues at all. Yeah, question.
Before, it seems like your padding is like, in hex.
Yeah.
Okay, so I was wondering, how are you encoding like the hello world? Is that like in a ASCII or?
Yeah, it sends across as ASCII just fine. It is strange that you don't have to match the formatting. Not quite sure what's going on with that. Yeah. Yeah. Scapy does have a lot of the things in the background handled for us. That's part of the reason why we used it and didn't just write it, because you could recreate this entire concept using just a straight HTTP library, but that's a lot of extra work. Scapy does do a lot of it for us. So I would not be surprised if it does actually get transferred at some point. Yeah. Any further questions? You mean the issue? Oh, you have a question behind you, though.
Oh, yeah.
Yeah.
You mentioned that if you had compromised the system upstream, that you could kind of like session jack and insert CNC to your regular browser. Were you actually successful in that, or did you only?
So that actually segues well with his question. We were really successful in virtualized environments. We have full control. This is very easy. Actual environments, it gets a bit iffier depending on the exact implementation people use, because there is actually a shockingly, well, okay, I can't say shockingly, we're nerds, a shockingly large amount of debate regarding the exact interpretation of the for future use of reserved bits. Some companies take that to mean let's reset them and delete them all. Others take that as we can do whatever. So the exact usage on hardware works in a virtualized environment, or the one we have at our house or the computer science labs, but not over the greater campus networks. Works sometimes over the internet. It's very odd as to whether or not it'll work in a larger scale. It's good as an extension of your existing library of tools. It's not really meant to be a standalone thing. So you can insert command and control into existing traffic. On an internal network, it's much easier to do. That's the very easy thing to do. We've had success with that. From an external network, depends on the external network, really.
Same goes for VPNs.
Oh yeah, VPNs are really weird because they reset your connections. They repackage everything, which makes sense. It's a VPN. You wouldn't want it leaking your information. Yeah. Any further questions? We did have a lot of fun experiences getting this to work on a college network that didn't really know what we were doing, and sending information across that the firewalls did not particularly appreciate, because it turns out college students like to torrent a lot of things, so they're not big fans of having peer-to-peer connections which have lots of weird traffic attached to them. So when you start bouncing them across, you start getting weird questions from the IT people asking, what on earth are you doing? Why are you sending broken packets across the network? We get emails. Stop it. So that's when we went virtualized, because we don't want that to happen anymore. We don't want to anger them. So yeah. Oh, another question. Got it back, then I'll come back to you. Yep.
So, based on IDS, what did you pick up because it's in a sense a non-form package? You're not most applications are going to use it for this, right?
No, most wouldn't, but a lot of IDSs don't check. That's the thing. You can look in Wireshark and actually see that these packets have been modified, but that's part of the debate with the whole whether or not the reserved bits are reserved and should be kept for future use. Because in theory, at some point they'll change, a lot of companies don't check them. They figure that they could be changed in the future and they wouldn't want to just murder their product accidentally. So that's, yeah. Yep. It's very easy to catch. It's incredibly easy to catch, and that's part of the thing we were talking about with the pfSense firewalls. If those bits are changed, you know someone's doing something weird that they shouldn't be. But it's an incredibly obvious thing that you can use as a data channel that no one really checks.
Going over the 6 bytes that you originally changed, and then I'm assuming you consider fragment packets for that TCP session that you then send whatever data you're sending over. What hash you send over?
Okay, we've sent over chat programs work really well over this. We've sent over we actually got a reverse shell working on another computer because we were able to send the information over an existing session. I believe that was actually a web server that we had. Yeah, that was one of the web servers. We opened up a website, and as the website was loading, when you sent out the request asking, I want this page, it's like, here, also run this command for me. And it could get the results back if you compromise the other computer, but you do not actually need to be able to see what the results are if you want to just rmrf/ a random web server without telling anyone. So yeah, we had a lot of fun and could do a lot more demos, but we don't actually have internet because we didn't expect internet, by the way. That was not an unplanned thing. We came into this planning to not have internet because it's a hacker convention. All right. Did you have another question?
Oh, yeah. I was wondering, now that you've gone through this level of research, are there any other fields or headers in packets that you think would be more covert if you have to do it over again?
More covert. Well, if one of the things we're actually looking at still is IPsec, which is encrypted IP traffic, does have a few other fields that could be played around with, and those are encrypted. You can't just read those. That's a lot of fun. But there are entire other layers that you can exploit and add more information into. The big thing about it is most of the places that you can modify without anything freaking out are just 1 or 2 bits. So you can add, say, flags and options and carry things across like that, but you don't get a very large amount of bandwidth, unlike with the padding where you can actually get a few bytes, and if you grab a few extra packets, you can get a few more bytes, and once you start fragmenting things, you can get a lot larger amount of information across. You have another question?
You haven't driven home the fact that you can actually send entire programs over this website.
I haven't driven home that fact yet? Oh, okay. Apparently I need to emphasize the fact that you can send across entire programs with this. You know, when we set up the reverse shell, you could actually send across an entire, say, bash script, although personally I'd recommend just using wget and grabbing it from somewhere else. But anyways, so you can actually send across... What?
It does include also the fact that if you also really wanted to, if you're deploying this out in a field and you decide you need an update, say you forgot an import or whatever, you could potentially send its own update through its own channels without anyone knowing again. Another fun method we've tried with.
That's right. Yes, that's right. When you do the code execution inside of Python, the Python script that's currently running can actually write its own Python script, then close itself, and then somehow also open itself back up again with the newly updated code. So you can send across, once you get the actual delivered payload from whatever you use to exploit the network, if you have a reverse shell put into it, you can send little bits of code over the channel and then update and add more imports. Say you wanted to import the, well, you'd have the subparse. Let's see, what would you want to import? Say you wanted to import your custom library for Bitcoin mining on whatever machine you've just compromised. Now you have your botnet on there. You could import that later, run the commands to pip install it all in the background using the covert channel. And well, if they're paying attention to their machine, they'll notice you have no traffic. And then you can have your botnet start issuing commands. Yeah. All right. Well, thank you all for coming. I hope you have fun at your convention. That was short.